Hello everyone, this is Dr. Hopkins narrating the next video in our series for Chemistry 472. We're still talking about first law, and this is we're going to kind of look at evaluating processes. Thermodynamics is the change in energy as you change a process or change in work and so forth. And so let's look at this. We have so first law analysis of a process. All right, so far, all we've talked about are closed systems. So remember, a closed system is one in which energy can flow through the boundary. So you can have work and heat flowing through the boundary, but no mass change. We'll get to the point where we add in mass change in open systems because it's particularly important when we're doing chemistry, because obviously the mass changes from one component to another and when you do a chemical reaction. This is a general review of all of our quantities. So we have internal energy, which is expanded in terms of T and V. It's also the statement of the first law. It's the change in heat and the change in work, so we can evaluate those. Then we have our new defined quantity enthalpy, which is expanded in terms of T and P. We have Cp dt in this partial derivative. And then we had our definition of work, which we derive from physics. So if you have a process that has everything that can change, then of course we have to evaluate this, and if it's not an ideal gas and so forth, we'd have to go through and figure out how to evaluate all of these derivatives and take integrals and so forth. But typically you set up the experiment so that you make things a little easier. So for example, what if we were only considering an ideal gas? Or what if we did this process isochorically or isobarically? Okay. Reversible versus irreversible, all of those things to consider. And so let's go to a couple of these cases. So if we had ideal gas, we go back for a second. So we have our expansion of our dH and du. And for an ideal gas, as you recall, the second part of the expansion of our internal energy change and our enthalpy change both went to zero, right? So those partial derivatives in there were zero. So the change in internal energy is just Cv dt, and enthalpy is just Cp dt. And then the work doesn't change, it's still the P external dV. If we do our process reversibly, well, now our work simplifies to minus P dV, right? So where our external and internal pressure are the same. And let's say we do the process holding something constant. So here we have ideal gas, reversible. Let's do it isothermally. So if we do it isothermally, dt is equal to 0. So naturally, du and dH are both equal to 0. There's no internal energy change and there's no enthalpy change if there's no temperature change, right? And then our work is equal to an opposite sign of our heat because our delta U is equal to 0. So dW is equal to minus dQ, or if you integrate these, which I have the integrals. And since we're doing our work reversibly, we can just substitute in PdV. We have an ideal gas, so we have the equation of state. We substitute that in. We have this integral of dV over V, which is, and I didn't put the limits on here, but this is the natural log of V2 over V1. So our work would be that. Our other two are equal to 0. And there we have our answer. And our heat is opposite sign, same magnitude. So we'd have all of our quantities from first law that we would know for an isothermal process, for an ideal reversible isothermal process. Isochoric, where we have dV is equal to 0, so work is equal to 0. So here our internal energy change is equal to our heat, and it's Cv dt. Our enthalpy change would be Cp dt, so we just need to know our heat capacities and our temperature change in that process, and we'd be able to evaluate all of our quantities. Isobaric, same thing. Here we have our pressure constant, so our work is just P, the integral of dV is just delta V, right? So we have minus P delta V. All right, so if we go on, and the most interesting case, or the one we're going to spend the most time with, is an adiabatic process. So we've talked about the three where we hold one of our components or our properties constant. In an adiabatic case, heat is equal to 0, so there's no heat exchange, but PV and T can all change. So we're going to consider an ideal reversible adiabatic process. Q is equal to 0 automatically. Anytime it says adiabatic, you already know that right off the bat. And so then our work is equal to our internal energy change. Once again, it's still Cv dt. There's nothing changed about that. It's an ideal gas, so these quantities are the same. DH, same thing. But let's deal with this. So if we have work, it's reversible, so we know that's minus PdV. So we equate these two sides, right? And then we can expand it, and we expand our work out. We include our equation of state, and I'm assuming that CV is constant in this case. So now we have nRT over V dV. Let's pull our t over on this side of the variable. So we're solving our differential equation by splitting the variables. As long as we assume that CV is constant, then this pulls out of the integral, and then we integrate from T1 to T2 and V1 to V2. We have those, and so those results are natural log of those, and that's the case. Okay, so then let's plug in CV over NR. So I'm taking my NR, putting it under the CV, taking away the negative sign and inverting this. So here we have CV over NR. I'm just collecting those together. The natural log of our temperatures, right, which is in natural logs. It's this case, right? These two are equivalent. And then this is equal to now V1 over V2 because of we've gotten rid of the minus sign. So let's go a little bit farther along in our derivation. So now we can get rid of if we go back, we get rid of our two natural logs, right, because they're the same. And we have T2 over T1, V1 over V2. And now I have put the exponent, I flipped it, right? So we have, this is CV over NR. If I put this to 1 over that, both sides, then you end up with this. So I did a couple steps before I went to the second slide. And then we can substitute in P1 V1 for T1 and P2 V2 for T2 because this is an ideal gas. Moles aren't changing, R is not changing, so those are equivalent. Okay, and then we can split our sides, and so we end up with P2 V2. Now I've done something a little odd, but I made this CV over CV and then put my V2 as NR over CV. Okay, so we're going to use this. We'll do it on both sides, which means we can then add those exponents, and then we end up with P2 V2 raised to the CV plus NR over CV, which, if you remember, for the constant heat capacities, the difference between CV and CP was in R. Okay, so then this is equal to CP over CV, so these two are the same. And so then we're going to define this CP over CV as gamma. And so in an ideal adiabatic reversible process, P2 V2 to the gamma is equal to P1 V1 to the gamma. And so what does this mean? If we compare, say, for example, an isothermal process versus an adiabatic process, remember an isothermal for ideal gas, PV is equal to a constant, right? So temperature is constant, nRT are all constant. In an adiabatic process, then PV to the gamma is constant. Well, now we know, because we know that CP is always greater than CV, that gamma has to be greater than 1. So that means that the relationship is going to be different. So in other words, the pressures, and then we have the statement below here, the pressure falls more rapidly in an adiabatic process versus an isothermal process for the same change in volume. And there are PV diagrams where you can look, and there's one in our book that shows this kind of process as well. And all of what we've done in this video, all of these processes have been for ideal gases. So how would you adapt them for real gases? You would have to use a different equation of state when we're talking about a reversible process and so forth. So it would be much more complex. So you can see this is the reason why we're often just using the ideal gas equation, because it's easy enough to manipulate. If we had to do a lot of these manipulations for the van der Waals equation, you can imagine how tough that were, how difficult that might get. Okay. So next time we will finish up a lot of our discussion of the first law analysis of processes.